do a little bit of recap. Oh, I'm sorry, Asim, I didn't call your name. I'm extremely sorry. Asim, how are you doing? I know that I've
That's okay. That's okay. Yeah, I'm good. I'm good. Doing fine. Had a great weekend.
nice. So Asim and we live in the same apartment complex in India, and he has been, you know, I have seen from a close distance as a student as well as a player. He's a great cricket player. I've learned a lot from him, and uh, nice to see you here, Asim, again. Hope you guys all enjoy this thing. Let's just get started. I'm just going to share a screen and we will quickly go over. So, are you able to see the session 3 slide?
I cannot see session 3 slide.
Oh, it's showing that, okay, yeah, please let me know. Okay, how about now? Still the same problem?
Okay, now I can
Yeah,
see.
now it's visible. Yeah.
Okay, cool. All right, and I think, again, it so happens I have also missed Shashwat. Shashwat, are you around?
Yeah.
Oh, I'm sorry, I didn't call your name. Apologies. So Shashwat is perhaps our youngest friend. He's in California. Um, he is in eighth grade, and he is extremely interested in mathematics. So um, thank you for joining. It's really early here. It's kind of cold, but I I'm really happy that you have joined, Shashwat. Thank you. Um, cool. So, without further ado, we'll just start with session 3. So, um, I'll just go over the recap, and then we have enough discussion points later today. So, I think one of the things that um, Asim asked me offline was about paradoxes, and Um, as much as mathematics is interesting, it's also paradoxical. So we will talk about paradoxes in perhaps fourth or fifth session in more detail. Um, but like I have said before in one of my slides, that a simple statement like this statement is false is paradoxical. When you begin to think that it is true, it becomes false. When you begin to think that it is false, it feels as if it is true. And um, it's very simple at a conceptual level, but what throws us off is that something as precise as arithmetic is also paradoxical at times. And we'll go into some of the details. I will refer you to excellent books on this fascinating topic. So we'll do that. I'm pretty sure that you guys perhaps were um, sort of um, thrown off by this particular abstract set slide. Perhaps you felt as if I tricked you. Let me just go over this one. So the point I'm trying to stress here, and Swara, this is something that you have expressed deeper interest into, comparing infinities. So what the argument that I made was that the infinity represented by the natural numbers is the same in size as the infinity represented by all rational numbers, that is fractions. Now, this seems really very spooky, and this feels very spooky. I mean, how can it be? Like Shashwat said, and there are so many fractions between 1 and 2. There are so many fractions between 2 and 3. And yet, the infinity represented by all of them is the same size as the infinity represented by natural numbers. Here is the argument that I made. There is no one-to-one correspondence here, but by this little trick, we were able to do one-to-one correspondence here. I'm hoping that this is, at least the argument is clear. You may not fully agree with this because we're playing with fire, literally. But are we all on the same page with respect to the argument that was made by Cantor?
I think so. At least I
Great.
am.
Cool. If this is not clear, please write to, on our group. We will discuss these things again, because this argument is really very critical, that we were finally able to get one order that helped us show a one-to-one correspondence between two infinite sets. And what Cantor argued was that as long as you're able to show that one-to-one correspondence between two infinite sets, they represent the same size infinity. And we'll get into this because we have another very important class to cover, class of infinities, and maybe the things will be clearer at the time. All right, so this is what we discussed. We spent a lot of time on this one, but I think we need to get this thing right. All right, so that's what we did. Now what I'm going to do is I'm going to transfer it to Apurva, and he's going to get us through the next parts. Let me stop my video, and I'll transfer it to him.
One second, I'm just setting everything up.
Cool. So I'll stop sharing. And Apurva, I think you should start sharing.
Can you guys see the slide infinite sets?
Yeah.
Okay. Okay, good. So, well, we know infinite sets. So, well, there are three types of infinite sets, or two types of infinite sets. They can either be countably infinite or uncountably infinite. And since we say that there's like one-to-one correspondence between two sets, if they are, um, yeah, if they have the same size, right? Then, if you can show that, then that makes them the same size, even infinite sets, right? So then, um, you can see if you can compare each type of set, the cardinality, to uh, the set of natural numbers, the cardinality of the set of natural numbers, right?
Mm-hmm.
And sorry, 1 second. Sorry, I there's a technical issue.
Are you not able to?
I can't see my own slides.
Uh, yeah, I'm also not able to see your slides, but is everyone else able to see his slides?
I don't think he's sharing right now.
Okay. Who is not able to see? I'm
One
not.
second.
Yeah.
Sorry.
I am not able to see your slides.
Okay. Upendra is not seeing. Maybe
Yeah, me
Apurva
neither.
just. Okay. So Apurva just stop all the. Or maybe should I show the slides and then you will
No,
talk?
no, no. I'll do it. Just one
Okay.
second.
Okay. Okay. Go ahead. No problem.
Okay. Okay, 1 second. Okay, can everybody see it now?
Yeah.
Okay, sorry about that.
He can see it. I'm still having some issue. Anyway, why don't you go ahead, Apurva? Just go ahead. Uh, yeah, if everyone else is able to see it, let's just go ahead.
Okay, so we can compare so depending on the cardinality of the infinite set, if we compare it to the uh set of natural numbers and get a one-to-one correspondence, then we can say that that set is also countably infinite. Uh, because there's a one-to-one correspondence between that set and the natural numbers, and the natural numbers are a countably infinite set. We know that they're countably infinite because we can count them, right?
Right, we can name them. We can just say that the first number is 1, second number is 2, and so on.
We can, yeah. So if you give me a natural number, I can tell you the next natural number.
Right, being able to count like 1, 2, 3 is an important aspect.
Mm, yeah. So, but if you have a set that is uncountably infinite, uh, you can't really. If I give you a number in that set, you can't tell me the number after that. For example, the real numbers, right? What's the next real number after 1? It's you can't really figure that out.
Right, I mean, I think the point is that any which way you look at, this is really the critical point, that any which way you look at it, you cannot name the successor of a given real number.
Hmm. Hmm.
See, we thought that this problem would be there with rational numbers as well, but this problem is not there with the rational numbers. With the trick that we did, we were able to order rational numbers without any ambiguation. But that is not true with real numbers. And we will see why in one of the later sessions. But for now, let's just go ahead and assume that real numbers, the successors or the predecessors, just cannot be named. We just cannot count. And that's why we give them sort of manageable name. We call the infinity of real numbers and uncountably infinite.
Yeah. And so now what I'm gonna do is so calculus needs a few definitions because like all mathematics, I mean, even though we can do some conceptual stuff in calculus, it's we can't just make it entirely conceptual. So there needs to be some definitions, some you know, uh, yeah, some definition pretty much. Uh,
Yeah, I mean, good definition. The point is
yeah,
that precision is really needed here. Otherwise, what happens is that we end up confusing ourselves.
yeah. And so I'm gonna tell you about something called a relation. And yeah, so in a relation, we have two sets. There's a domain and a set called the codomain. Now, this relation maps elements from one set onto, or really the domain, onto the codomain. And, but, so many of you might have heard in, like, I think algebra that, so a function has a domain and a range, right?
Yes.
Yeah. So the domain is relate. So a function is actually a type of relation, but uh, more generally, actually, relations have just a domain and a codomain. The codomain is different from the range of a relation. There's an important distinction between them, as I'll show in here. So the so depending on how you define the domain and codomain, the range may be a subset of the codomain. As you can see in that diagram I drew at the bottom, we defined the codomain and the domain are both integers, but not all integers in the codomain are pointed to by uh, an element in the domain. Because, for example, 3 it does not have uh does not no and has no integer, but it really there's no
Th-
integer when doubled gives 3.
There's no integer in the domain that will map onto 3 with the relation double,
R, yeah, R go 8 to 2, yeah.
right? I mean, so again, we what we are trying to do is that we're trying to be precise. That's the way the things happen in mathematics, right? A relation we ever you understand, right? Relation, like there are human relations, there are social relations, there are relations because of behavior. There are all kinds of things that happen in our real life, but we want to make them precise, and that's what I think Apurva is trying to do.
Yeah. So basically the range is basically the subset of the codomain that is mapped to by an element in the domain. So the codomain can contain elements that are not mapped to by an element in the domain, but the range cannot. Every single number in the range is mapped to.
I like that
Um,
idea.
yeah,
So range is like an image. Basically, what happens is that you hold the mirror in front of the domain, take an element from the domain, look at its reflection, and that reflection has to be in the range, but it doesn't necessarily have to be in the codomain.
yeah. Um, so Yeah, did everybody understand this? Because this is a little tough topic. Hey, and yeah, feel free to unmute whenever you want to ask a question or speak. It's all free, don't worry. It's you don't have to raise your hand or anything. Mm. All right then. Um yeah, so the first type of relation that we've probably all heard is a function. Now, these are two there I've shown two functions here, and the third diagram is not a function. But can anybody tell me why the first two are functions?
The first two, one one element in like the set of A only maps to one element in B, but in like the third one, three maps to two elements in B, and like one domain value can't map to two range values.
Yeah, but it it still works if, for example, in the first one, if 5 is not mapped to anything, or if in the second one D is mapped to by two elements. It's still a function. But for in the third one, 3 cannot map to A and B, right? So then that's a function.
Yeah.
Yeah, that kind of relation between two sets is called a function.
Yeah, it's a
Again,
type of relation.
right. See, mathematics has got words. We need to get these words right. We need to all be on the same page. Why the first two are this thing called function, and why is the third not the thing that we call a function? So first two are functions, third one is not, and we need to be agreeing to this.
Yeah. And there are four more types of relations. But I feel like the one we've come across the most currently, and probably in the future too, is the function. It's definitely very important in calculus and uh, even algebra if you've taken it, high school level algebra.
Yeah, absolutely. I mean, function is what everything kind of revolves around. We need to have a very good understanding of mathematical functions. What Apurva is trying to do with these two sets, domain and codomain, on a coordinate plane, what do you guys think? How would we say something is a function? On a coordinate plane, on an xy plane, on a Cartesian coordinate plane, what will you tell me about function? What is a function? Is a line is a function, right?
Yeah.
Is parabola a function?
Yeah.
Hmm.
What about circle? The equation of the circle is x squared plus y squared is equal to r squared. Is this a function?
No,
Why not?
because for one x value, there are two different y values.
Hmm.
So that's a very good point. So that's exactly what the third um, diagram on the right we are trying to look at, right? So we are saying that for one value of x, it has to have one value of y. And this kind of a thing can be captured by what is called a vertical line test. So what does that mean? That whenever we have a function that we have plotted on a Cartesian plane, for one value of x, we need to have one value of y. If that litmus test is passed by your relation, then we call your relation a function. So now this might be confusing for some of you because we have been always told that okay, circle is a function because there is an equation between x and y. But the way we should look at it is that a particular portion of circle is a function. For example, consider that the quadrant of the circle that has been bounded by the first quadrant. Is that a function?
Yeah,
Why is that a function?
because at that point it's just like an arc where one x value has only one y value, and there's like yeah.
Right. So basically, this is called some kind of a, again, some technicality. You can ignore it, but it's kind of important to know that I'm always going to say that x and y are all non-negative. There is no value of x and y that is negative that we are interested in currently doing. Then we are okay, right? We suddenly say that for any value of x, there will be one and only one value of y. For example, x squared plus y squared is equal to 25. And both x and y are greater than or equal to 0. Then what will happen? There will be no value of y which is negative or x which is negative that we are interested in entertaining. And then everything seems to fall in place.
Yeah.
Cool. Go ahead.
Um, yeah. So there's so another type of relation is actually called a total. Okay. So again, first two are examples of a total, and the third one isn't. Um, can anyone same thing? Can anyone tell me why the third one is not a total?
Go ahead, Upendra.
I don't know for sure, but I think maybe because in the third one, not all the numbers are connected to the variables.
Or yeah, that is correct. But we should say that not all the elements in the domain are connected to an element in the codomain. For example, 2 is not connected to an element in the codomain, but even though 3 is connected to 2, 2 is not connected to any. So we say that it is not a total. Okay?
Yeah, so
Okay.
if you're looking at all these things for the first time, it will definitely be a little bit confusing.
Yeah,
So I suggest that Apurva, you also share your slides,
I
and
will.
you guys should just go ahead and put these things on paper when you review the slides, and these ideas will become a little more concrete. Again, this is a technical part. You know, there is a name for this in mathematics. It's called rigor. So we need to be rigorous.
Hmm.
While we enjoy the concept, like Apurva said, conceptually it is very enticing. As we start doing that, we also need to understand and accept the importance of a rigor. And we're slowly introducing this because, fortunately or unfortunately, calculus needs this kind of a rigor. So don't lose your interest, don't get bogged down by these things. It'll all fall in place. Let's just make progress. Come on, go ahead.
Okay. So there there are a few more types of uh relations, but these you don't these are not hardcore terms that you need to remember. They're nice to know, but they're used very little, first of all, and second of all, you can whenever you want to see about them, you can just search them up on Wikipedia or basically Google. You can just search it on Google and everything comes up. But it's still good to know to see the patterns between the function and the relation, and to know these other types of relations too. So the next one is called an injection. Mm, and again, same thing. Two uh, examples of injection, and the third one is not an injection. Mm. Anyone tell me why?
Because in the third one, C is mapped to by both 1 and 3.
Yes,
So many to 1
exactly.
is not allowed.
Yeah. Um, so basically, yeah, even though 3 is maps to A and B, that in an injection we're not looking at the domain. We don't care how many uh elements each element in the domain map to. But in the third one, C is mapped to by 2. Uh I think, yeah, 1 and 4. So the in the injection, each element in the codomain cannot be mapped to by more than one. It's
Yeah,
less than or
just
equal.
not allowed. What is allowed in function, for example, you can have two different elements from domain can go to one element in codomain, and that is not allowed in this kind of a relation that we just happen to call injection.
Yes. And yeah, so now we went sort of from looking at the domain of a function to looking at the codomain of a function, right? How many elements are mapped to, rather than how many elements an element maps to. So yeah, there's so another type of relation is surjection, and again, this looks at the codomain, how many elements in the how many elements each element in the codomain is mapped to by. Now in the surjection, it's uh, like very similar to the previous things we've seen. Now I again ask you, like, why is the third one not a surjection but the first two are?
Because D is not mapped to anything.
Yeah, exactly. Yeah, D is not mapped to anything in the third one. So, but because in a surjection, each element needs to be mapped to by at least one element. It can be mapped to more than one, like C is, but it cannot be not mapped. Each element in the codomain specifically. Right. So that's the yeah, perfect. Now, the last type of relation is a very important one. Now, it may sort of overlap, but it, it really comes in handy a lot. Even though we don't formally learn about this in calculus or even in really any part of grade school. I haven't learned this in any of my math courses, but this it's a very important type of relation, and it's called a bijection. Now, the the special thing about bijection is there's always a one-to-one mapping between the domain and the codomain, as you can see in the diagram. There is each each element in the domain is mapped to exactly one element in the codomain. Right? So, mm,
So these why is bijection important? Because it is found in real life so often. For example, a person and their fingerprint. We believe that there is a one-to-one correspondence there in this. A person and their retina. That's going to be one-to-one correspondence, right? It's not only important because of this one-to-one correspondence, but there is much more to it, and I think we'll come to it. But again, we are trying to formally define what a bijection is.
yeah. So yeah, that we're just trying to, yeah, basically have a formal definition. And yeah, I know these are a lot of definitions, but I try to summarize it in this slide. And so it's, I'm not going to spend too much time on this slide because it's a lot to read and you don't have to read the whole thing. But as long as you understand what these five types of relations, uh what makes them basically, why can you say a relation is an injection, or why is it a function? And there's an interesting question here. Can a relation I give you, suppose I give you a relation, can it be a function and a surjection?
I think it can be because if in a surjection each element is mapped to by only one element, then it'll be a function.
No, the in a surjection the element in the codomain is mapped to by at least one. It can be more than one, but it's each element is, the point is each element is mapped in a surjection. This, the point is, these all these relations are just ways to relate elements of one set to elements of another, right? But I believe that there can be any relation can be multiple of multiple of these types of relations. For example, for function and surjection. Can a relation be a function and a total? What would be the requirement for a function, a relation to be a function and a total?
Like the total, each domain has to map to only one instead of mapping to more than one.
Yeah,
In that
it
case, we
huh.
both a function and a total.
Yeah, exactly. So it can, the point is, for it to be a, for the relation to be a function and a total, it has to map to exactly one element, or it can, it it can map to only one, exactly one element in the codomain, no more, no less. Right, okay. Now I just want to say, this is the arrow diagram I've shown, and uh that I've shown a few before. And so we say that this arrow diagram has greater than or one equal to arrow out, because each element in the domain has at least one arrow pointing out. So each element in the domain has greater than or equal to one arrow pointing out. And we say that this arrow diagram also has less than or equal to one arrow in, because each uh, element in the codomain has less than or equal to one arrow in. We could also say that this arrow diagram has equal to one arrow in, because each element in the um, codomain has one arrow in. Did everybody get that? This is an important convention that I'm going to be using. Okay, everybody got that?
Yeah.
Okay. Um, then I am going to go to the next slide, and using this convention that I've shown, can we summarize the requirements for a relation to be a function? What would be the requirement or requirements for a relation to be a function in terms of the arrow diagram, the features of the arrow diagram, like the number of arrows in or out?
Less than or equal to one arrow in
For,
function.
yep, good. That's That's correct. How about a total? Anybody?
I'm not sure if this is correct, but like greater than or equal to one arrow out.
Yeah, yeah, that's correct. Great job. And how about injection? Sorry, I saw that.
I saw it, so I mean
Yeah,
technically, limit
yeah,
and
no worries.
less than or
Yeah,
equal to one arrow. In I think.
sorry, I didn't hear. Less than or equal to one, right?
Yeah, one arrow.
Okay, yeah, and everybody saw that. It's all right. And how about so now we talk about when we talk about how many arrows are going into the codomain. We usually when injection basically talks about how many arrows are going. It basically looks at the codomain. So we have to look at how many arrows are going in, right? So similarly, a surjection should be anyone?
I'm kind of guessing, but greater than or equal to one arrow in.
Yeah, that's correct. And but does everybody understand this like this convention of the arrow diagrams and using the number of arrows in and out to to define the relation?
Yeah.
Yeah. Okay. Um and the last one is a bijection. Now this is again special, but this one should be pretty easy. Can we define uh how many arrows in or out for a bijection?
I think it's just one arrow in and one arrow out.
Yeah, either one or both. Yeah, one arrow in equal to one arrow in and equal to one arrow out. Always for a bijection because it's a one-to-one map. And yeah, that will come up pretty often. Not specifically in the term bijection, but it's important to make this connection in the future. Um, so yeah, we'll probably come back to this in the future, but just you should know that it's a special type of relation. Yeah. Now I want to talk about. I'm just gonna briefly talk about some types of functions. I believe I hope many of us have learned this in school. There are a few types of functions. They're yeah, just algebraic, exponential, logarithmic, trigonometric, and hyperbolic. Now this is very brief. This is also very technical. We can find any of this on the internet. So I'm not going to go very much into this. Just there are a few types of functions specifically. Now a function is a type of relation, and now there are types of functions. So but we categorize these because functions are used extensively in calculus. And yeah, now this is I'm just not gonna spend too much time on this. This is I hope many of us know this already. And if not, you can just see the slide or search on Google. It'll give you a lot of information. And it's not like I'm gonna these are the specific types are gonna be needed like too much yet. It it's not gonna be needed too much yet. So I just briefly go into this. Now I have a question for you. Is a bijection a function? And how about a total, surjection, or injection?
I think a bijection is a function because each value in the domain only maps to one value in the codomain. and that's
Okay, so and
and,
so yeah, yeah, go ahead, sorry. My bad.
and in function that's basically the rule
Yeah, equal to 1 out is bijection and function is
less than or equal to one in.
yeah, exactly. So a bijection is a function, but is a function a bijection? If I give you a function, can is it a bijection?
I don't think so because a function, the wait, let me think.
Hmm.
Well, not every function is a bijection. Some functions can be a bijection.
Yeah, okay, that's an interesting answer. And so yeah, there are some functions that can be bijections, and some functions are not bijections. But all bijections are functions. And yeah, how about a total? Is a bijection a total?
Wait, what was the total thing again? I forgot.
Yeah, it's a yeah, no problem. It's the for a total, the requirement is greater than or equal to 1 arrow out, right? You
Okay.
understand that? Yeah, good. So is a bijection a total?
Yeah, because a bijection can a total says there can be one arrow out, but and a bijection always has one arrow coming out. So
Yes. So a bijection is always a total, right? That's what you're saying?
yeah, yeah.
Okay, now is a total always a bijection?
No, not always. In
Again,
some
yeah.
cases.
In some cases it is, some cases it's not. Yeah. Now there's an interesting question. If a relation is a function, is a total function, okay? It's both a total and a function. Is it a bijection? If it is both a total and a function.
Can you repeat the question again, please?
Yeah. If the so if a relation is a total function, right? It's both a total and a function. Is that relation a bijection?
I don't think that it always is a bijection because you can still have two separate elements in the domain pointing to the same element in the codomain.
Yeah. So even if there's one arrow coming out of each element in the domain, there can be more than one element. There can be more than one arrow going to an element in the codomain. That's what you're, is that what you're saying?
Yeah, that's what I'm saying.
Okay, yeah. Yeah, so I I think yeah, there that's correct. Believe I can come up with a relation that is a total function, but it's not a bijection. And I hope you guys can come up with it too. It might take a little bit of, thinking, but it's definitely possible. Yeah. Now, how about a surjection or injection? Bijection? Are they Is a bijection a surjection or injection? And just to recap, surjection is greater than or equal to 1 arrow in, and injection is less than or equal to one arrow in.
Can you repeat the question?
Yeah, is the point? The question is just that is a bijection a surjection or an injection?
Yes, it is.
Both surjection and injection. Yeah, because it satisfies.
Yeah, it
Yeah,
is. Yeah.
because it satisfies both the conditions greater than or equal to one arrow in and less than or equal to one arrow in.
In fact, bijection is the only thing that satisfies both surjection and injection. See, these are the things that are related with the rest of the mathematics. This is how we do things. This is, in fact, one of the ways in which we prove something. We show something to be greater than or equal to 1. At the same time, we show that it is less than or equal to 1. Now, if that is the case, then the only value that satisfied is it is 1.
Yeah, yeah. So yeah, if something is greater than or equal to one and less than or equal to one, then it has to be equal to one. Yeah. Now there's now an interesting question. If you have a relation, okay, that is a total, a function, and an injection, does it have to be a surjection? And you can get a piece of paper, a pencil, write it down, see if create some error diagrams, see if you can make a a function, a relation, right, which is a total and a function and an injection, but not a surjection. Just is it possible, even if uh, you can't find an example, do you think it's possible? Yeah, that's a good question. And if you want, um, yeah, why don't we just? That's a good question. I'll just put it on the WhatsApp group, and uh, you can just think about it and put your answers there. Yeah, we should, yeah, we'll discuss about that. And at any time, if there's a question or anything, just feel free to unmute. Like, you don't have to raise your hand. Uh, if there's any question. So I'm just gonna go ahead. That's an interesting question, but it's it will just help you understand the different types of relations better, and relations in general better. But it is not related to what I am going to go on to, which is this so an interesting operation on a relation. Okay, suppose we switch the domain and codomain of a function and reverse the direction of the arrows, okay, is the new relation, let's call it an inverse relation, is it still a function? Remember, the initial relation is a function, but is the inverse relation a function?
In some cases, it would be a function, but in other cases, it might not be.
Yeah, so that's okay, but in this case, does it seems to
Yeah,
be a function, right? In this case.
yeah,
Yeah. Yeah.
it is.
Now, how about in this case?
No, it won't be because
No.
in the inverse relation, C maps to two
Yeah,
values in B.
yeah. Yeah, so we can see that there are functions, right, for which it will work and where it will not work. It depends on the function, right? So the question is, what are the requirements for the inverse relation to be a function?
There must be one-to-one correspondence.
Right, so we come back to,
Bijections.
It has to be
sorry,
a bijection.
it has to be a
Bijection.
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 It has to be a bijection for the inverse relation to be a function. And if the inverse relation is a function, we can just call this inverse relation an inverse function. So we have functions and inverse functions, right? Now, no, but the main point is that um, only if it's a bijection can the inverse relation be a function. That's
But
yeah,
if you have a non-function, then you take the inverse of it, it could be a function.
it could, yeah. Now that's definitely true. For example,
So
yeah.
it could not be a bijection, and then you inverse it, and it could still be a function.
But specifically for a function, when you take its inverse, for that relation to be a function, the function has to be a bijection, right? Do we get that?
Yeah.
Okay, yeah, but that's correct. It if there is a relation which is not a function, the inverse relation could be a function. Um, yeah, is there? Do you have an example, or what? Like any type of relation that when when taking its inverse, it could be a function?
On the slideshow, like given in the second box, like the one where A has the variables and B has the numbers. If you take the inverse of that, you get a function.
If you take the inverse of that,
Yeah.
yeah, so the inverse of the second box would be the first box. So the inverse of the second relation would be the first relation.
Yeah. And like
It
the
would,
second
right?
currently is not a function, but when you
The
take
second
its
relation.
inverse, it becomes a function.
Yeah, yeah. Now, but if you took a say a total, okay, um, and you took its inverse, could it be a function? The inverse of a total. Yeah, that's a yeah. Um, that's a little bit tough question, but I could there are so many of these type of questions because it's just easier this way to relate the different types of relations, and even in make when you even take their inverse, right? Now there are plenty of these questions, and yeah, if you have any idea or anything, you can, or if you can think of the requirements for the inverse of a total to be a function, yeah, if you find those, then yeah, feel free to send it on the WhatsApp group. But I'll go ahead, because there's so much I can do with this, and there's not enough time. But now we've done a lot of theory, like definitions, right? And
I mean, I'm sorry to interject, but you guys all did very well. This is slightly challenging, too many definitions, but yet I think you were able to hold your interest. Obviously, you had to go back and hone these things so that we are able to tell ourselves exactly what these relations are and what happens when we invert them. And why Apurva has spent so much time on just inverting will be clear in one of the next sessions. This is really very important. I mean, when we try to, for example, differentiate certain functions, the invertibility of those functions becomes really very important because certain things becomes very easy. And that's why we want to get these things right in our minds.
yeah, so but this has been a lot of theories. So let me ask you an interesting question. Okay, there are so many interesting questions um this session, but this is a really nice question that will lead us into um the heart of calculus, really. Now, how do you find the area of a circle without calculus? Now, those who have learned calculus may know a way that uses calculus, but try going back to before you knew calculus and think about how you would solve this problem.
Pi r squared.
Yeah. So, yeah, but let's go back to like the time of the ancient Greeks. They never knew pi, right? The Back then there was no constant, there was no mathematical constant called pi. But somehow the um, Archimedes was actually able to relate the area of a circle to some measurable quantity. So can we express the area of a circle as a ratio? Like, okay, and the one thing I have to say is there is no there's no one correct answer. Like, you could have there could be multiple different answers, but I do have a specific answer in mind.
I mean, just to give you a little bit of background, Greeks were less interested in absolute values. They were more interested in
In
values which are related to others. So, in other words, ratios. Like if I have a certain figure, a geometric figure, how big or small it is with respect to some other geometric figure that I know about. So they were more interested in relative things rather than absolute things.
I'm not sure like the exact stuff of it, but I think it has to do with like you take the slices of the circle and when you line them up, they form like a rectangle, and there's some relation to do with that.
Yeah, that's exactly what I had in mind. The Yeah, we cut the circle into sectors, right? And then we use them to form a shape that looks like a parallelogram. Like, as I've shown below, the shape it's not really a parallelogram. It looks kind of like a parallelogram, but it's definitely not a parallelogram because the top and bottom surfaces are curved, right? So, but we can again rearrange the parallelogram. The weird shape that looks like a parallelogram to make a weird shape that looks like a rectangle, right? As I've shown. And now this weird shape, right? We can say that it has a top side or bottom side, which we call S, okay, and the a height which we'll call H. Now, um, can we determine what's H, what H is, or what S is?
I think H is like the radius of the circle, and S is like half of the circumference.
S is half of the circumference. Yeah, yeah, that's yeah, I believe so. And the it, that's now at this point it seems pretty exact. Now S is not the distance, the straight line distance. S is actually the total distance, because even though I've shown it straight, it's uh, I what I meant by S is the total distance along the curved shape, the top side of the curved shape, which really is it's not a straight line. Yeah. And so, but now, what would the next step be to finding the area of the circle? Because using this, can we find the area of the circle? Can we exactly find it? Because how would you find the area of this figure? The exact area of this figure using the dimensions we found.
You would just multiply SMH like a normal rectangle.
But is it a rectangle? Because it's a weird shape that looks like a rectangle, right? But so the area of the rectangle might be different than the area of the shape, right? Is there any step in the middle that we can have to make it easier to get the area of the weird shape? Can we do something else? Mm, yeah, so for example, suppose we added more sectors into the circle, right? Suppose we added more sectors into the circle and made the same weird shape. Now this weird shape looks more like a rectangle than the previous one we had, right? So we can think like, so if we increase n, right, that means more sectors in the circle. And the more and more you increase n, the more and more this shape will start looking like a rectangle, right? Does everyone agree with that?
Isn't this kind of what they did to find pi, like before Newton came in with the binomial theorem?
Yeah. Now this actually gives the ratio that was used to find pi. Yeah. And the that's yeah, before that exactly what you said, but the only thing is that, like, back then they didn't have the computing tools, I mean, that were good enough to find pi as we know it today. So back then, the ancient Greeks, all they did was represent everything, right, as ratios. For example, we can do the same thing for c, right, the circumference of the circle. But for now, we can consider that a measurable quantity, since we can say use a tape measure to measure the circumference. Say.
Sorry to interrupt, but Upendra, you raised the hand. I mean, just go
Oh,
ahead and
sorry, I didn't see that.
Yeah, I also wanted to say something that the Greeks also used hexagons, like really what do you call it, accurate hexagons to represent circles. So instead of just doing it through the slices, they just put hexagons in the circles and then represented one circle with multiple like accurate hexagons, and then divided the hexagons into triangles and then calculated their overall circumference. So they had like the approximate circumference of a circle.
Yeah, that will be the approximate circumference of a circle. But how can we really represent a circle as a hexagon? How accurate is it really?
Well, it depends on how fine the hexagon really is. I mean, how tiny should the difference between a straight line and a curved line be so that you can represent a hexagon as a circle? That's the question basically, I think.
Right. I think, all these are really good ways of looking at this thing. I mean, finally, it is going to boil down to what you just said, Upendra, that, what at what point are we going to approximate a curved line by a bunch of straight lines? What is that is going to enable us to do that? And we're trying to, kind of go toward that. Is there a formal way in which we can say that this is it? I am satisfied with it, and so should everyone be. And we're progressing toward that particular point that will allow us to do this. So this has been, really, really stimulating discussion, but we're also a bit out of time. It's already 10 minutes more. We can definitely continue if there is interest. Apur, what do you think? How?
We'll continue for a few more minutes. If everybody's all right. If you need to leave, you can leave. If you have some other commitment. But I just have a few more things I want to show you today. And
Is that okay, everyone?
yeah, I just okay.
Yeah.
Cool. Go
Okay.
ahead.
Then so yeah, we this if you increase n further and further, it starts looking more and more like a rectangle. It's not a rectangle yet, but is everybody on board with the fact that it starts to look more and more like a rectangle?
And
Definitely
less and less and less like that weird figure
like
that
that
we had
weird shape.
before.
Yeah, so definitely the weird shape with more circle sectors looks more like a rectangle than the previous weird shape we had with only 8 sectors, I believe. This one has 16 sectors, the new one, and the previous one has 8 sectors. So it seems like the one with 16 sectors looks more like a rectangle, but I just want to make sure everybody's on board with that. And if somebody's not on board with that, please speak up, and yeah, we'll yeah, we'll clear the doubt.
I have a question. So this would mean that we're approximating the value or like the shape of the rectangle. So it's not exactly a rectangle, but it looks similar. So we're just approximating at that point, right?
Yeah, we're just saying that if you add more and more sectors, it starts looking more like a rectangle. That's that's all we're saying right now. We are not saying it is a rectangle. We are not saying it's a rectangle yet. And uh, but we're not saying it's a rectangle, but we're saying it starts looking more and more like a rectangle, right?
You agree with that, Upendra? And I think you're on mute. That's okay. Okay, go ahead, Apur.
Yeah. So the next thing is, uh if we increase it further and further, okay, now think however high you can get, okay, we increase an arbitrarily large, we make an arbitrarily large, we just increase it further and further and further, okay, and so to say, we never stop. Now in this case, it approaches the rectangle and it starts looking more and more like a rectangle, okay. Now this rectangle that it starts looking like, what will the height of the base of the rectangle be?
Well, the height is the radius of the circle,
Hmm. So
and
r. Hmm. Go ahead. In the base,
I'm pretty sure that's still the circumference of the circle, like half of the circumference,
half
right?
of the circumference of the circle. So we'll call that c by 2. And so what will the area of the rectangle be?
C by 2 times r.
Yeah, exactly. A height r, base c by 2, and the area of the rectangle is rc by 2. Now, yeah, I think, yeah, I'll just close here. But I think we're out of time, so we'll
Yeah,
just.
and we'll not look at, again, we will try to be, or we will act like Greeks. They didn't know what the length of the circumference is, and we will pretend as if we don't know it too. But we can definitely say that at some point in time, we will have a circle which is cut like this, which start looking like a rectangle, will have an area which is equal to r times c by 2, where c is the circumference of that weird thing, which looks more and more like a rectangle. That's all we're
Mhm.
going to say. Our claims are very modest at this point. We are not getting any absolute answers because we don't have them.
Yeah, yeah. So, um, yeah. What I'd like to leave you with is the question: if we increase n and further and further, okay, we increase it as much as we can. We just don't stop increasing it. Will this weird shape that we saw, right? This weird shape. Will this weird shape be can will it become a rectangle? If we increase it further and further, will it become a rectangle? Because we know it starts looking more and more like a rectangle. But the question is, will it ever become this rectangle that we found with height r and base c by 2?
I don't think so because even though like each sector is getting really, really small, like it's still gonna have a little bit of arc at the top. Like for example, take a tangent. If you have a tangent of a circle, it only meets the circle at one point, not at multiple, and like so it won't meet at multiple points, right?
Okay. Yeah.
It's there's still that tiny arc.
Yeah, there's still that tiny arc, yeah. But um, if you get take it closer and closer, okay, it will start to look much. So the difference between the area of the circle and the area of the rectangle will reduce further and further, right?
Yeah, so I think the doubts are going to remain in your minds. It just I think we are kind of having something like a deja vu where we were asking the same question in one of the first sessions that okay, is 0.999 dot same as 1? Some doubts are going to remain, and if we stop this process, we are not going to have 1. But we agreed eventually that the non-terminating decimal was the same as 1, and in the same spirit we are asking this question, that we take enough sectors, will this be indistinguishable? Will the circle become the rectangle?
Well, the circles. So if you like, if the radius is the length, if you were to say, and the width is like an infinitely small section,
Yeah.
if you,
Yeah.
uh,
Right.
if it's differentially small, then you'd be able to represent the area of the circle by adding those
Right.
rectangles with the infinitely small width, and that
Right.
would give you the area of the circle, and that could, I think, be represented by a rectangle.
Cool. I think that is a fair statement. I think we all agree with that. Um, but still, it's not enough. I mean, we need this rigor, we need this formalism in order to stand on firm grounds. And I think we are going to, perhaps you guys, I mean, it's not a big secret, but I think what Apurva is now trying to do is to introduce to us, reintroduce to us the concept of what we call a limit. When we say that, when can we say in the limit? Phrases like the limiting condition. In the limit that something have some value gets arbitrarily close to some other value, what happens? When can we say that and still be very, very firm? I think we are going to start with this particular thought. We are going to leave you with that particular thought for the week, and we'll discuss these things more and more. But this is sort of reflection, kind of of a question, that what really in mathematics lets us use these phrases freely in the limiting condition, or as extends to get arbitrarily close to something. Can a function of x get arbitrarily close to some other value? Now that you have good definitions of functions, can we extend or use those definitions to define more things like what we call a limit? So we will continue this exciting discussion. Uh, I think we have covered a lot of ground. Did you have more, Apurva, to cover? Oh, you are on mute. Sorry.
I think yeah, we'll do that next time. I had some more, but we should do that next time. This is a good place to end.
Yeah, great. I think, again, thank you guys for your time. It has been close to an hour and a half, I think, but we're okay. I think we talked for about 1 hour and 10 minutes. Uh, Thank you very much again. Please don't hold yourselves back. You guys all have great questions and great thoughts. So
Yeah.
please use our
Oh yeah.
WhatsApp groups. I think I had a lot of fun. And I hope you guys too. All right.
Mhm.
All right. So see you next time. Just one quick question. Next time is Diwali, so I don't know. I think we have time. In fact, we might have some free time, and so are you guys all okay with 23rd?
Yeah.
Cool. So if there is no problem, we'll continue on the 23rd then.
Okay.
Perfect. Thank you very much, and you have a great day or night, as
Yeah.
the case may be. Bye.
Bye.